So it's recording now. What I'll do is just pick out some, this is the book, if you bought it or not. I'm just going to pick out some problems from chapters 1 and 2 with structures, and then we can just start counting. So the question was, so finding unique carbons and hydrogens, and I'm going to draw two structures up, so that'll give you time to draw them as well, and then we can look at this question. Can everyone see that all right? Is it fairly clear? So I think the thickness of the pen's all right, from my end at least. So here are two compounds, and again, this is from chapter 2 of Klein, but in regards to the question that was asked, let's find the unique carbons and hydrogens for each. So we'll basically figure out the C's, the H's, and then the ratios of them. So maybe I'll so everyone knows what I'm referring to, I'll call this A, and then this B. So let's look at A first. How many unique carbons do you see? I can tell that screen's really high because you all look like you're sitting in the front row of a movie theater and your neck's like, it's weird. Before, the screen was like closer to the whiteboard. So for A, how many do we think? Got some 3s, some 4s, some 5s. Need to do like the Price is Right, or that little dude's climbing the mountain. We need to keep going. It's more than 5. So yeah, let me ask you a question. How many carbons total are in this molecule? There's 9. So there's 9 unique carbons. So we have some people that are avalanched by that answer. Let's go through it. And so what I'll do is I'll switch the color over to like red, and I'm going to put it like a dot next to each one. So definitely what you want to do throughout this course in general is, I see a lot of people going like this. You want to write stuff down and sort of count it somehow, whether you're using a dot or a number or something, because your eyeball's going to jump around and you're going to like miss something or count something twice. So what I'll do in red, I'll put a dot next to each unique carbon. I'm going to start by the methyl group that's bonded to the carbonyl. So here's 1. We go over, there's 2, 3, and then I'm just going to walk around this ring. 4, 5, 6, 7, 8, 9. So this ends up being 9. So why is each one unique? Because there is no symmetry in this molecule. There's symmetry in one sense. So you're looking at the plane of the projector. Within the plane of the screen, the molecule is symmetric. But orthogonal to that, it is not. Does everyone follow that logic? That means basically, so within like this plane, this carbon like the top half of that carbon mirrors the bottom half. It's like you're slicing it in half. But there's no mirror plane like orthogonal to it. And that's really what you need if you're going to reduce the carbon count from what the total number of carbons is in the molecule. So that's 9. How many unique types of hydrogens are there? So I've worked with some students in office hours and whatnot, and a question arises, does the unique number of carbons always equal the unique number of hydrogens? And the answer is no, and you'll see why in this case. What do you think a reasonable answer is? I've heard 2 people say 6, so we'll use that as the majority. So in blue, I'll mark them off. You have a CH3 group here. And so I'm only going to mark the ones with unique hydrogens in blue, but we'll go around the ring. So we're going over to this carbon next. That has 0 hydrogens. So immediately now you can't have a maximum of 9. That number's smaller. You go over again, so this actually has a little laser on it. So this, you go there, there's no hydrogens there. So we'll go around the ring this way and just put blue dots next to the ones that do. So that one does, so that's 2, 3, 4, 5, and 6. So this one's going to be 6. And so in terms of the ratio, you're just counting how many are in each one. What's your question?
If the molecule is like symmetric, would the 2 carbons at the bottom of the benzene ring be the same types of carbon? Like not the very bottom, but the ones on the side.
So the question was the 6-membered ring that has the 3 double bonds in it, that's called a benzene ring, just so you know what we're referring to. And the question was, would some of the hydrogens on there be equivalent if the molecule was symmetric? And yes, the answer is yes. And you'll see that when we look at compound B. But let's go ahead and look at these ratios here. We were starting with this methyl group over here, and then we're just going to count, and then we'll record those numbers. So that's 3. Then we go along the bottom of that ring. So within the ring, there are 4. And then we finally have the methyl group bonded to the oxygen, and that's another 3. So we have 3 here, 1, 1, 1. Then at the top there's 1, then over here there's 3. So how do you want to sort of study for this in general for this semester? I could write an exam based on like 1 molecule and ask you 25 different questions. So you want to start yourself thinking about what those questions are. So can you name 2 functional groups that are in this molecule? So a ketone and an ether. So here is the ketone, and then here is the ether. So based on visual inspection of that molecule, even though it's getting sort of crowded, how many degrees of unsaturation do you count? Just looking at the molecule, how many degrees of unsaturation do you count? I heard a 2. Heard a 5. How many people say 5? I see a couple of timid hands, confident hand. So it is 5. So can you tell me how we counted to 5? What are we counting? How many pi bonds? 4. How many rings? 1. So as we delve deeper into learning more things, I could ask other questions, but now we'll sort of move on to compound B and do the same type of analysis. So why don't you spend, say, 2 minutes, figure out the number of C's, the number of H's in the ratio, and we'll circle back, record that information. How many unique carbons do you spot? Let me give you a hint. This molecule has a plane of symmetry that is orthogonal to the projected screen. So therefore, it's going to reduce it from 9. It's going to be 7. So let's walk through that so we all see it. So again, having a model kit will definitely help you with this, but also being able to, I don't know, visualize things. Have you ever taken like a learning inventory assessment? No one? So I can send out a link where you answer like 15 questions or something, and it tells you if you're more like verbal or visual or whatever. It sort of helps to identify deficiencies that you can make up. So let's go ahead and count these. So here's 1, here's 2. Then we're coming to a carbon that has no hydrogens, that's 3. Now what I want to do, so that you see how it reduces from 9, we're going to look out sort of in both directions from that carbon that I just put a dot by. So we're at 3. This carbon here and that carbon there are equivalent. Does everyone see that? So if we're looking here and we look out, we see this carbon, we look out, we see that. Those two are equivalent. We go out one more, this and this are equivalent. Then you get to the end of that ring, that's its own thing. And then finally this methyl group is its own unique carbon. So I'll, when we're done with this, I'll put up the 3 possible scenarios for that type of ring, and you can see how the symmetry affects the carbon count. So let me just write a note so I don't forget that. Okay, so let's do the number of hydrogens next. What do we think that is? Yeah, it's 4. Does everyone see that? So why don't you tell me the ratios? We have to record now 4 numbers.
3. One.
Nope.
2.
2. And then what's the last one? 3. So we have here 3. These are equivalent, so that's 2, 2, and then 3. So again, why are you learning this? What's the relationship between A and B?
Your structural isomers.
They're constitutional isomers. So they have the same molecular formula, but different connectivity of the atoms. Yes?
I just have 2 questions. Are we gonna, obviously we need to know like the ratios, but are we gonna need that on the test? Like whenever we test questions, are the ratios?
Yes.
Okay, and also how do you know, I'm confused on the hydrogens, like how are you supposed to just know that like they cancel, the carbons cancel?
That it's symmetric.
Okay.
Is that what you're asking?
Okay.
So you're looking for like a mirror plane. So what I'm going to do on B in green, I'm going to draw a dotted line down the middle of that molecule. So maybe it'll sort of slice it in half. And this is where you're probably going to think I'm lying, but if you had a model, it would make more sense. So I'm going to draw a dotted line running down this axis here. So if you can think of it 2 ways. If that was a mirror, one side equals the other. It may not look like it, like this oxygen can't mirror a carbon because they're not the same. But basically, the way it's drawn, it's flat on this axis, right? But what you have to accept, and we'll study a little bit more, is that this bond, which is a sigma bond, can rotate. So instead of that carbonyl being in this plane of the projected screen, it's rotated out towards you. And so therefore it's in that green dotted line, which is the mirror plane. So that mirrors itself. But the ring, when you bisect it like that, this carbon here and that carbon there mirror each other. So that means they're equivalent. And so that reduces the carbon count and the unique set of H count. So the same thing happens over here for this group next to this oxygen. Maybe let me draw something before other people ask questions, just so I can sort of like see how you're thinking about something. So this molecule that I just put up there is butane. What is that molecule? The one right below it. It's butane as well.
Yeah.
So it may sound like a trick question, but some students will say that they are different because they are drawn different. But what you have to recognize is that for every sigma bonds can rotate. And now in this lower form, you can sort of better see that plane of symmetry that I just drew that green line through. So these would be equivalent to one another, and then these would be equivalent to one another. in that top form, it might not look like they are because it's sort of like zigzag.
Are structural isomers and constitutional isomers the same thing right now? 'Cause I've been watching videos and they've been using those two terms synonymously.
I would stick with the term constitutional isomers because that's more explicit about their relationship. There's all sorts of isomers. You're going to learn a lot of them over the course of this semester.
In A, B, are those like cis-trans isomers?
No. So cis-trans has specifically to do with alkene geometry. Yeah.
Can you like draw out the hydrogens like using a first?
Oh, with the blue dot.
Yes.
So there's 3 right there.
Okay.
There's 1 and 1, so that gets that set of 2. There's that second set of 2, and then there's 3. So this also has the same ketone and ether. Let's look at this. Yeah.
Do you want us to know the difference, like, to be able to tell if it's cis and trans and internal and all that?
Not yet.
Okay.
More of the nomenclature stuff will be later on, I think in module 2 or something. But for now, you need to know hexane through decane, like the carbon count. Anything other than that is not yet. So let's look over at this disubstituted benzene problem. And what I want to do here is just point out the mirror planes that are present when you have molecules like this. So maybe what we can do is first assume that this group here is a methyl and that group there is a methyl in each case. So methyl and methyl. Now why don't you think about the number of unique carbons in each of them? So I'm gonna call these just, I'm gonna call this O, this M, and this P. You don't have to memorize that. It's just something I'm gonna call them now so that we know which one I'm talking about. And again, these are constitutional isomers of one another. So they have the same molecular formula, just different connectivity of the atoms involved. So for the O isomer, how many unique carbons do you count? Eight is the total carbon count. We got a 7. We got a 6 or a 7, 6.5. So one thing this class will do is you are you. You have your own viewpoint in life. You know what I mean? So this class is going to sort of knock you out of you, making you 2.0. So you're going to start viewing things a little bit differently and not so rigid. you want to get out of very rigid thought patterns. You want to be like flexible. You know, I put up that picture of Mike Tyson knocking that guy out. You want to zig and zag a little bit so you don't get knocked out. You know what I'm saying? So the O isomer has a plane of symmetry. Can you spot it? And I'm guessing the reason you can't spot it is how it's drawn. What's that? It starts between the two methyl groups, and it then sort of runs diagonal across that molecule. So let me draw that in green here. So we're looking, our eyeball is sort of here, that's our eye. And what I'm going to do is draw that mirror plane. So in red, what I'll do is identify the carbons. So there's the methyl groups, they're the same. Then we're sort of going down the methyl groups at the same time. These are the same, that's 2 sets. These are the same, that's 3. These are the same, that's 4. So what about the M isomer? How many do you see there?
4.
Don't fall into a trap. This is the second round with Mike Tyson here. You got to be fresh. The molecule does have symmetry, but now it's sort of a different plane of symmetry. See on that O isomer, the plane bisects a carbon-carbon bond. In the M isomer, it bisects a carbon atom. What's it? Someone said it? It's 5. So your eyeball is here. Granted, that's not the most straight mirror plane ever. So let's start with the one our eyeball hits first. So this is 1. Then we go out. These are the same. That's 2. These are the same. That's 3. These are the same. That's 4. This is its own thing, so that equals 5. All right, now for some razzle dazzle. We're going for the P isomer. Don't get knocked out. What? No, you're knocked out. What? It's 3. So why is it 3? Because this has 2 elements of symmetry to it. So let's look at it 2 ways. Your eyeball can be up here, looking down this, or it can be here, looking that way. So that's 2 different orthogonal mirror planes. So if you look, the methyl groups, those are the same. You go down, those are the same, so that's the second set. Now you go out, this is the same as that, but if you do it the other way as well, that's the same as that, and then those end up being equivalent. So it's 3.
So it doesn't matter how you divide this one?
What's that again?
It doesn't matter how you divide that one?
Well, you're gonna wanna look at those specific planes, like those mirror planes.
You have enough practice where like you can just look at these structures and just like immediately 3, 4, 5.
I've done it enough. I mean, I'm so again.
Like, do you have little heuristics that like you pay attention to and it tells you?
I don't know. I've written enough of these. I've looked at enough. I've been doing this like over 20 years. I'm no smarter than anyone in here. I've just seen more than you have. So don't let the rate at which an answer is produced discourage you from learning. You'll eventually get it. It just takes time. Really, what all of this is about in the big term is like recognizing patterns, and that's what like the functional groups are. So once you see how certain things are connected, you say, okay, that's an ether, and then you start learning the reactions of that. So let's go through real quick and do the number of hydrogen count for each, and then you'll see that it's also not equal to the carbon count. So for the O isomer, how many unique sets of hydrogen are there? Yeah.
On P, why wouldn't it be four unique carbons? Because when you get to the methyl, like the lines of the methyl group, why wouldn't those be one? Like after they mirror each other, why wouldn't that be the fourth one?
So maybe what I'll do is draw this on the board so that you can maybe visualize it better. So on this axis, if you had like a rod or something, and you rotated this molecule around, you would see that these mirror each other. So like this mirrors that, and then this mirrors that. So that's actually bisecting the carbon atoms themselves. But on this plane, it's bisecting the bond. And so what you would see is that now where we drew this, like this dot, this would mirror that. And then, if I said that would mirror that. But we know from here, these are the same. These are the same. Now when we do it this way, these are the same, these are the same. So those all end up being the same. It's almost like, I don't know, like I sort of see things like, I don't know, maybe if let me draw this and see if this makes sense. So I sort of like drew like the top half of this molecule. So if you had this axis and you spun it around, it would redraw the bottom half, which would be the same thing. I don't know if that makes any sense or not. I'm sure there's like a mathematical way of describing that as well that might give you more satisfaction. So what about the O isomer number of hydrogens? 3. What is the ratio of them? So yeah, I would say 6, 2, and 2. So you have 3, 1, and 1 times 2 gives you 6, 2, and 2. What about for the M isomer? How many unique sets of hydrogen do you have? Someone's throwing me a 4. So it is 4. You have this one here, that's 1. This one here, that's 3. 1 and 1. So you have, we're kind of jammed up here, 4. Now keep in mind, the ones on that mirror plane, they're not doubled, so they end up just being 1 and 1. So we have 6, 2, 1, and 1. Then what about for the P isomer? How many unique sets do you have? There's 2. And the ratio is what? 6 and 4. So I do lab research and we write papers. So I'm actually writing a paper on sort of this like topic for teaching. Maybe I'll share it with you guys and get your feedback. You can be as brutally negative on this paper as you want, because I encourage the feedback so that when it gets reviewed, I'm ready for the sting. But the way your book teaches this is very different than the way I show you here, because your book's going to go into how does the machine work. Like, I don't know how my car works, but that doesn't prevent me from driving to work every day. So this is more conceptual in terms of like not making it as like boring, I guess. So, well,
Question.
yeah.
So on the P, why don't you count all the carbon, like where it says 4, you only count it 2, 2, why wouldn't it be 8, which is, you know what I'm saying?
For the hydrogen count, or
Or the, you know, where it parentheses,
where it's 6 and 4.
why is it 4 and not 8?
So it's, I guess the most straightforward answer to that, this group here and that group there are both methyls. So that's they each contribute 3, so that's 6. How many hydrogens are on this carbon? Just 1. Yeah, so that's another thing you'll need to sort of be aware of is the hybridization. So what I'll do is we'll sort of move away from this problem now. We'll advance in a fresh slate here, and we'll take another question.
A lot of the homework has a bunch of intermolecular forces stuff on it. How relevant is that to the field what we're working on, like for this particular test?
It's a smidge relevant. There's a couple problems where you definitely have to know those things. Maybe we'll just do a problem from the book and you'll get a flavor of what you need to be able to do. So let me just capture this here. So here's 5 compounds. So intermolecular forces are like a description of things at the atomic level that affect the physical properties of the bulk matter. So like, why are things solids? why are they liquids or why are they gases. So you can really give a qualitative description based on looking at the bonding pattern of whatever the molecule is. So the first thing, the first compound here is CH4. So, you know, a question was before, can you look at something and tell whether it's polar or nonpolar? Like, I can at this point. It's, again, a skill that you need to develop as well. So CH4, is that a polar or nonpolar molecule? So it's nonpolar. So let's maybe draw it out in a different way so you can see why that is. So here's a representation of that molecule. I haven't talked too much about this in class yet, but you know, everything's sort of a preview of the next thing. I'm sort of highlighting the central carbon. What do you need to know in terms of this convention? This C is carbon. This thing here where these bonds all meet, that is a carbon. Again, that's not a very accurate description of reality. If you could shrink yourself down to the atomic scale, you would not see like a C in space. It's not like a letter C. You really probably wouldn't see anything because there's so much distance between the nucleus and the electron clouds. I don't know. If you're into science stuff like IBM, Bell Labs, basically they have things, these very powerful microscopes that can see down onto the atomic level, where you can actually almost see orbitals at this point, which is pretty neat. But this is all just part of the convention. So you're going to be given a periodic table. It has some numbers on it. What do you need to know? Fluorine's the most electronegative. It all points towards that. So this is nonpolar because there's really not a difference between C and H electronegativity. So
0.5, like anything more than 0.5 is a difference.
yeah, so if you take the numbers of electronegativity and you subtract them, anything more than 0.5 is you start to get polarity of the bond.
Are we needed to know that? Like,
Well, as we go through this problem, that will sort of explain like what you're asking. So what is a covalent bond? Covalent is sharing. So the C and the H are sharing those electrons, and they're doing it pretty equally. So it's nonpolar. Methane is really not attracted to itself, so at room temperature, it is a gas. There's nothing taking one and attracting it to another. So if you think of a gas as particles floating around, when you start increasing the functional groups that attract one another, that's when they start condensing. Then you get a liquid phase, and if it's ordered enough, you get a solid. So that's how those things affect the physical state. So what about ammonia? Is that polar or nonpolar? So it's polar. So let's draw out. I'm going to draw this in sort of a way I haven't drawn before, just so it mimics the methane. So I actually sort of drew a line going up to that lone pair, and that's important for the following reason. So you're saying it's polar. If you had to write 2 or 3 sentences why, you could do this sort of analysis. So the nitrogen has a lone pair of electrons. So we can assign that as delta minus. That should be just pretty intuitive why that is. So the hydrogen is going to be delta plus. So each of those are delta plus. Each of those has a bond to dipole. And the way you represent that is that sort of the plus starts where the delta plus is and points to what's negative. And again, that's probably not like the best representation of things, but a bond dipole is a vector. And what do you need to have a vector? Have you taken physics? You need a direction. So like a direction and a magnitude, right? So you have 3 bond dipoles, and they're basically the sum of all of those is like pointing up, and it's reinforced by that lone pair of electrons. So what does it mean to be polar? That there is like a really big molecular dipole. So what I've just shown there, that's an example of an intermolecular attraction, which methane does not have. The lone pair of nitrogen on the ammonia is attracted to the delta positive H. That attraction makes those 2 molecules come together. So that's why ammonia will have a different boiling point than methane. Yeah.
So when you're looking at determining whether it's polar or non-polar, so I was getting a little confused because I saw that nitrogen had the formal charge of -3, and then it has 3 hydrogens, so it'd be +3. So I was thinking non-polar, but you would just be looking at the group.
So
The group.
maybe I can just correct something that you just said.
Yeah.
It doesn't have a formal negative a -3 charge. So this symbol here that I used, this delta symbol, you don't want to think of that as like a formal charge in the sense of like -1 + 1. You want to think about it as if you could plot like the electron density of that bond, the electrons are more towards nitrogen than they are the hydrogen. So that sort of increases the I don't know, the electron density around the central nitrogen. Yes?
Is that hydrogen bonding right there?
Yeah, so this is an example of hydrogen bonding. And that's the primary intermolecular force that causes these things to change physical properties.
Would it also be something with the dipole forces, or?
Yeah, you could rationalize it like that way as well. The dipoles are attracted to one another.
So, essentially,
So that would be a dipole-dipole attraction.
So what would be the hybridization of the nitrogen?
So that's a good question. What would be the hybridization of the nitrogen? So you say sp3, you say sp2.
It's SP2. It's SP2 because the one pairs out after the bond.
It's sp3. The reason it's not sp2 is what is the molecular shape of ammonia? It's a trigonal pyramidal. If it was trigonal planar, then it would be sp2. That lone pair of electrons is polarized towards one end of that molecule. If it was sp2, the lone pair would be on 2 different faces, and the molecule essentially would be nonpolar at that point because the dipoles themselves would cancel out. Yeah,
It's not exactly 109 at the top.
it's probably deviated from that.
Deviated is the electron.
Yeah, so the lone pair will compress the bond angle to some extent, so it'll be less than 109.5. you need to know what the hybridization, like the normal bond angle for whatever hybridization. So there's 3 types of hybridization, there's 3 bond angles. Maybe we'll just write them down right now.
Do we need to know how to break bonds and all that?
Like, break them? Like, what do you mean?
Like, there's some, in the Safford, there's like problems where it was like, which bond is the strongest, and you know, really calculate how.
You don't have to do any calculations just yet.
Okay.
That's like chapter 6 or something where you actually get into the math of it. You do need to have a qualitative understanding about like the ranking of bonds. So let's do this first, then we'll do that. So here's the hybridization. What's the bond angle? What's it for sp2? What now? And then sp. So you do need to know that, and that falls out directly from the orbitals that are involved in making those hybrid orbitals. How many sigma bonds does an sp3 hybridized atom have? sp2 and sp. So what makes up the difference? So with sp2 and sp, so the pi bonds, you kind of jam it in here. So this is just 4 minus whatever, so that's 0. 4 minus 3 is 1. 4 minus 2 is 2. So water is polar. So I think we all agree with that. Dihydrogen monoxide. So maybe so let me throw this at you to ponder. What hybridization would you call that? Oxygen. So how can you like unstuck yourself in identifying it when it's not carbon? Look at what we just did. So we said that an sp3 hybridized atom has 4 sigma bonds. You want to think of that lone pair just as like a sigma bond. It's not involved in a pi bond, so there's like 4 sigma bonds, so it's sp3 hybridized. The reason it's not sp-sp is that those lone pairs would then be they would be orthogonal to one another, 90 degrees in p orbitals, and that's not the case. Yes?
Why, what's the point of doing the like shaded or like the filled in and dashes? Like what is the point of that?
So what is the point of doing the...
And it's just like a visual thing?
So you would agree that these 2 things are in the plane of this board. I said before that writing methane like this is like a lie, because that's assuming all 5 atoms are in this plane, which they are not. And then these bond angles would then be 90, which they are not. So really what we're doing is trying to represent that it's sp3 hybridized, where that bond angle is 109. So this wedge is meant to be like coming up towards you, and then the dash is going behind the board. So that more represents or resembles the actual molecular geometry. So sort of the same thing, water would have a molecular dipole like that. After you sum the bond dipoles, the lone pair electron dipoles,
What hybridization did you say it was?
sp3. Here's a little, I always like to put like a little twist in the exam. There is nothing that is sp4. sp4 is not the answer. That needs to go on a shirt. sp4 is not the answer. What's the name of this next compound? Carbon dioxide. So you're exhaling it now. So it's sort of neat. You probably never thought about this, but like, where does the carbon of the carbon dioxide come from that you're exhaling? It comes from the glucose that you eat. The glucose goes through metabolism, and then those carbons are excised and oxidized, so you're exhaling it. If you think about the amount of gas you exhale, like if your liver and kidney had to process that, you'd be sitting on the toilet all day long. I mean, you'd never get up. So CO2, what is the hybridization of carbon? So what's the molecular geometry? It's linear. So the hybridization is sp. So this is one of those where you really have to draw it out so you count all the electrons for the Lewis dot rules. So is carbon dioxide polar or nonpolar? So it's nonpolar because you see that we have delta minus, we have delta minus, we have delta plus. Even though each bond has a dipole, collectively they cancel each other out because they're pointing in opposite directions.
What kind of bond is that?
What's that again?
Remember that molecular force?
So the carbon is sp hybridized. You have 2 sigma bonds, 2 pi bonds. So the molecular geometry is linear.
I didn't know if you wanted to say like the London dispersal and all that.
Like the dipole.
Yeah, that's, I don't know. That's boring.
It'll really be on the text.
I don't mean to like pull the old bait and switch and like 90% of the tests be on London dispersion forces. No, that's not really on there. There's a question up top. Yes.
I was wondering, does it still experience dipole, or is it just London dispersions as it cancels out?
Well, I mean, so overall it's like non-polar, but it's still going to have an attraction to itself, but it's not going to be like great because you're exhaling it now, it's a gas. So the attraction between 2 molecules of CO2 isn't really that great. So the more non-polarness wins over any sort of like London dispersion or whatever.
Simple question, but both of the oxygens are agreeing to the octet rule, and that they're having 6 in total, right?
They're do what now?
Both of the oxygens are obeying the octet rule.
Yes.
Right from that. Okay.
Yeah.
Because it's like the 6. What am I trying to say?
If you look at the total contribution of each atom,
Yes.
so it's based on the group number, so 6, 6, and 4. So that's the total number of electrons you need to show, which we are. So the next molecule has been banned. It's not good, but they used to use it like in dry cleaning. So if you think about what dry cleaning is, they're still using a solvent. They're just not using water. So this molecule was used in dry cleaning. but they can't use it anymore because it's like bad for the environment. Yeah, question over here.
Hang on, what is it about that written down? It's about, it has to do with C2H6 and why it's bent, or like in the video that you sent, it talks about eclipsed and, eclipsed and
Staggered.
staggered, yes.
So yeah, go on.
So the bond between the carbon and the carbon is it bent?
So let's finish this, then I'll get to that because it's maybe tangentially related.
Okay.
So CCl4, is it polar or nonpolar? So again, it's nonpolar. So you have a bunch of lone pairs here. Each carbon-chlorine bond is polarized, but all four of these dipoles cancel each other out. So this ends up being nonpolar. And the reason it makes a good dry cleaning solvent is that grease, which your clothes get dirty with grease. Grease is nonpolar, so like dissolves like. This basically cleans your clothes. So the reason you don't want to use water when you dry clean something is that a lot of fabrics will like shrink. So you don't really want that, especially with your fancy stuff. Yeah.
So what would be the intermolecular forces in that?
In carbon tetrachloride, I guess they would be the London dispersion forces. So what are those things? Again, we're representing like a lone pair of electrons as two dots, but really it's like a cloud of probability. And the electrons are like moving like with like torque. When something twists, it torques. That sort of creates like a temporary negative charge that's attracted to a temporary positive charge. So that's the dispersion. So it's very fleeting. Like a dipole is permanent. The dispersion force is fleeting. It doesn't exist long. So let me just get back to this question about, say, the bond angles in something like ethane. So there's the next homologue, methane ethane. So your question was about the relationship between basically hydrogen atoms on different carbons. Is that?
And every angle between every atom in that molecule is 109.5.
Yes.
So I think I'm struggling to understand why it's bent.
So was this a YouTube video I linked to you guys or something? Is that? So that's probably, we're going to study that, but not like right now. So in ethane, the bond angles are all pretty much 109.5. The question you're asking is about, if I basically called this, if I called that carbon, or that hydrogen A and that B, the bond angles we've been talking about include 3 atoms. So say, for example, hydrogen, carbon, hydrogen. That bond angle is 109.5. Hydrogen, carbon, carbon, 109.5. The question you're asking about is this HCC H here. So that involves 4 atoms. That's a different type of angle that we haven't talked about and will be on a future exam.
So it's more like a descriptor because
It is. It's talking about the relative location of 2 different atoms.
tetrahedral.
Correct.
But those, so we're getting into that later on where we're getting descriptors from those.
Yes. Yeah.
Can we run this by boiling point?
Yeah, we can do it qualitatively. I don't know the exact numbers. So the question was, can we rank these by boiling point? What would you say is the highest boiling? So water is the most. You know, if you look at room temperature, you have methane, ammonia, and CO2 are gases. I'll tell you that carbon tetrachloride is a liquid at room temperature, so that would be the next one down. So this would be, if we were ranking these increasing, this would be 5, this would be 4. CO2, what do you know about CO2? Is it a liquid, ever? No. It's a solid that sublimes, so that never has a boiling point. So I think between ammonia and methane, this would be 3, or 2, and that would be 1. So
So I have a question. Did you rank their boiling points based on the intermolecular forces they had?
that's what you use. That's the principle behind that.
What was the question?
Who said that?
What was the question?
She basically asked, when we ranked those, were we looking at the intermolecular forces? And so that's what you're looking at. So what is an intermolecular force? You're basically looking at the difference in electronegativity between 2 atoms, if there's a polarized bond or not. What? Qualitatively speaking, yes. So there's, I don't know, like this fear of, I gotta memorize boiling points for compounds, and that's not like a useful exercise for anyone, because you don't benefit as a human being for knowing the numbers of these things, you know what I mean? It's better that you understand like the concept behind it rather than memorizing numbers. So if you're given a selection of compounds, you should be able to do like this sort of analysis and say, okay, this one will be the highest boiling of all of them. Yeah, up top.
So ammonia has hydrogen bonding. How's that not the second highest boiling point?
So the second highest will be the carbon tetrachloride. So the reason for that, even though it's nonpolar and it doesn't have these intermolecular forces, and again, don't take this as like gospel, but the weight of those chlorines add to, it being in a condensed state. Normally, you can't look at a molecule and say, oh, this one has 2 more mass units, so it will boil higher. That's not necessarily true. The main thing really is the intermolecular forces. But the fact that you're adding these chlorines, that weight does give it that property.
So how will we know when to determine like boiling points based on the molecular forces or the mass?
The question was, how will you know when to use intermolecular forces or something like mass? I would say of a 25 question exam, at most you're going to see that like once. So I wouldn't put too much like energy into like that specific thing. You know what I mean? Because it's not going to pay off for you in the exam. On any exam, one question is 4 points. You know, don't like die on the hill, as they say. If you're sort of like stuck, take your best guess. The thing with the if at, you're essentially getting, you know, 2 additional tries for points. If you take all 4, you get nothing. So your bonus is like built into that. If this were a regular exam, if you're filling out a Scantron, you're either right or wrong. So if you're wrong on your first try, don't freak out. Like reconsider. Like, okay, I thought it was this, but I'm wrong. So what's the next best choice? You know, you have minutes per question, 60 minutes, 25 questions. It's like 2.3 minutes or something per question. Like, don't overwhelm your brain and try to just, I need to remember all of this, and then you get flustered, and then you start scratching off the wrong line, and then that's how mistakes get made. Question up here. What's that? Sure, yeah, let me write up a structure here and we'll look at it. So does anyone know what melatonin does? So it facilitates sleep. So if I'm not feeling all right, I might take 1 or 2 of these. I don't know if it necessarily has like an effect. These like you get those like buy it at CVS like melatonin. You could probably eat them. You know what I mean? To me, it doesn't really work. So you can look at this and visually count the pi bonds and rings. So what would you say the number of rings is? And then the number of pi bonds. So yeah, I see 5 here. So that gives us a total of what? 7.
Well, could you do it like without like having the structure in front of you, like how you did it earlier today in class?
Yeah, so let's even though we've already done it, let's sort of just start from the beginning. Why don't you count the carbons, hydrogens, nitrogens, and oxygens? I'll write that down, then we'll go from there. Even though we know it's 7, we're just going to verify it. How many carbons do you see? How many? So I see 13. Hydrogens? How many? I feel like my high school algebra teacher. He'd always turn around and be like, how many? So 16. Nitrogens. Those are pretty easy to spot. And then oxygens. There's 2. So pretend that you were just given that molecular formula on the exam, and the question was how many degrees of unsaturation are there? So you're not seeing the structure at this point. So let's take this in sort of two separate, different things. When you're given a molecular formula, you have to like reduce it to just C's and H's. Oxygens do nothing to the hydrogen count. So we can sort of come up with a revised molecular formula here. We're just getting rid of the oxygens. Do you remember what nitrogens do to the H count? So each nitrogen subtracts one hydrogen. So this is our revised molecular formula. So now N is equal to 13. So if you had 13 carbon atoms, you have to figure out how many hydrogens there would be if the molecule were fully saturated. And to do that, you're going to use what formula? Which is what? CnH2n plus 2. Which should be that, I believe. So C13H28. Then you're going to take this one from over here. Maybe I'll use the highlighter. You take this. Oh, that's not good. So again, this is sort of my own wonky algebra or math. So the carbons will always cancel out. You're left with H14. And if we recall from up here, a degree of unsaturation is equivalent to a molecule of H2. So we're going to divide that by H2, and that's going to get us 14 divided by 2 is 7.
That's just another way to find it.
It is.
Okay.
And so that's primarily going to be the way moving forward, because I like to, huh?
The second one?
Yeah, I like to crank it up a notch. So if you think about like the obvious things, and that's what like this class is about, is you're given something that looks simple, but there's a lot of information in there. So what do I mean by that? C13H16N2O2 has 7 degrees of unsaturation. You're going to learn about mass spec, IR, and NMR starting next week. You're going to be given data. You will be able to look at that data and start making connections to functional groups. So let's look at melatonin. What functional groups do you see in there? So yeah, this is alkene. We can call this an amine. So let me, I don't want to like scare the shit out of you or anything, but let me just, like I said, organic chemistry is not the hardest thing you're ever going to do in life. You're going to be presented with other things that will make this look like nothing. So let me just give you a preview. This isn't going to be on the exam, but you're going to enjoy this very much. So in infrared data, you would see a signal at this number. It would be blatantly obvious, and you're going to make a connection between that number and that functional group, carbonyl. Then you're going to go, I know that a carbonyl, I can see it there as a pi bond, that's 1 degree of unsaturation. We know that that molecular formula has 7 degrees of unsaturation. The IR is saying that there's a carbon and an oxygen worth 1 degree of unsaturation. So I know that that fragment exists. So the remainder of that formula now has 6 degrees of unsaturation. Then I can look at other pieces of data and pull different fragments out. And I will take this thing here, and I will eventually get at that structure through everything I've learned in this class. So even though it's a simple molecular formula, when you're given the data, you will be able to figure out what it actually is. So maybe we'll take one more question and then we'll wrap up for tonight.
I have a question about something that was going to be on the exam. I remember you saying something about for the functional groups, do we need to know like the different like what degree they are? Like if it's a 1, 2, 3, or 4.
You do for the alkane.
Okay.
So you know methyl, methylene, methine. Methyl is primary, methylene secondary, methine is tertiary.
Okay, yeah.
The other ones not so much. We'll get more into that when we learn nomenclature and it becomes a little bit more important. The other ones really you just need to know the bonding pattern and what the name is. Question over here?
I was going to ask, how in depth is the naming going to be?
Not very in depth. If there is naming, it's pretty obvious.
On the test,
Do what now?
maybe on the test.
Yes.
Pretty obvious.
Again, I'm speaking from my own brain bias of having written the exam and coming up with these questions as a mad scientist. So my objective is to challenge you, but to not discourage you. And again, the reason we're using the if-at form is so that you learn, right? So if you don't make the right choice, you get a second choice and you learn from it. So again, don't freak out. When I taught 255 last semester, there was a student that sat in the front, and I could see the spectrum of emotions on her face, from joy to like rage to sadness. I mean, just be calm. You have plenty of time, so just titrate yourself. Yeah. So these two jokers over here, Sydney Boyd and Caitlin Burkhoff, are part of the ACS student affiliates. They're going to have a study session over in the library, room 242A. Is that correct?
Yes.
So there's whiteboards and stuff in there. So if you have time, they're going to start at 7 p.m. and run till they shut the library down. I don't know. No, they have it reserved until 9. So if you want to do more studying, it can be helpful to work at a board on problems. They're going to go over there soon as well. So that's 242A in the library. So you do need to know what resonance is. So sort of review that so you know what that means. There's going to be a couple questions on that on the exam. So if we're good, we'll see y'all tomorrow.